A large object about 10 light years away moving toward Earth.
The first alert pulsed across scientific dashboards long before news anchors learned how to pronounce the strange designation. 3I Atlas, once a dim and distant visitor wandering silently through the outer darkness, suddenly brightened in some observatories and vanished from others. That discrepancy alone would have been unusual, but it was the follow-up data that shattered the calm of the astronomical community. A cluster of automated telescopes registered a luminous flash, a sudden swelling of reflected light followed by a dispersal pattern consistent with catastrophic fragmentation. Within minutes, cross-checking teams realized that the object had not merely brightened, it had exploded. Before we start, smash the like and subscribe buttons for more updates. The expanding cloud of debris glistened against the void like a cracked jewel scattering its facets, and the earliest analysis triggered a cascade of alarms. Trajectory modeling systems redlined under the strain of trying to process the fast-multiplying fragments. Observatories scrambled to adjust and optimize their tracking, but initial calculations showed that the debris field was widening faster than any predicted tolerance window. The object had been on a grazing inbound path relative to Earth's orbital lane, and in its disintegration, countless fragments had inherited portions of that vector. The uncertainty tightened rapidly. The implication became impossible to ignore. A portion of the debris was coming directly toward the planet. What had once been a single icy, inert traveler from the deep interstellar wastes had transformed into a dangerous swarm of rock, dust, and volatile compounds. Scientists who had tracked 3I Atlas for months found themselves watching their familiar data turn into an evolving threat map. No one had expected such a dramatic structural failure, especially from an object that had shown such stability earlier in the year. Yet the readouts were undeniable. The explosion was not the gentle shedding of material common to certain comets as they warmed. It was a violent, full-body rupture, the kind typically associated only with rapid outgassing, internal stresses, or a collision with something unseen. As each fragment's vector sharpened under refined calculations, tension mounted in every research center tuned into the analysis. The debris was not a cohesive cluster. It was a chaotic fan of trajectories, each piece following its own inherited direction. Some were drifting harmlessly into interplanetary space. Others were tumbling unpredictably. Still others, the most concerning of all, had settled into a projected corridor that intersected Earth's orbital position within a calculable window. The projections were treated with urgency but also with care, because modeling the motion of dozens, then hundreds, then thousands of fragments was an exercise in managing probabilities. Each fragment, whether a millimeter-wide shard or a boulder the size of a small building, carried its own mass, reflectivity, and spin. It might veer from its path after a minor sublimation event or collision with another fragment, but the trend line persisted. Enough debris converged within the corridor that it became statistically improbable for Earth to escape unscathed. This realization reshaped conversations in real time. Astronomers who had been accustomed to academic debates about interstellar objects now found themselves addressing scenarios that blended orbital mechanics with planetary defense strategies. 3I Atlas had already been a rare visitor. As only the third confirmed object to originate beyond the solar system, it captured public imagination with thoughts of distant star systems, unbounded cosmic drift, and the mysteries of galactic motion. But now the fascination had transformed into something more primal. A visceral awareness of vulnerability in the face of a celestial event no one had anticipated. The explosion raised more questions than answers. Some theorized that 3I Atlas might have been structurally compromised long before its approach, perhaps fractured by ancient collisions in interstellar space. Others speculated about hidden cavities of volatile ices buried beneath its crust that could have destabilized under solar heating. Still others considered the troubling possibility of a collision with small, untracked objects within the solar system's outer region. Whatever the cause, the result was undeniable: a debris field with enough mass, velocity, and diversity of composition to represent a genuine threat. Even though much remained uncertain about the exact number of pieces on an Earthbound course, the mere possibility drove rapid coordination among global monitoring systems. Orbital prediction software was recalibrated to focus specifically on high-risk fragments. Radar arrays prepared to acquire targets once the pieces moved closer. Agencies with experience in tracking near-Earth objects shifted personnel to full-time monitoring. What had been a scientific curiosity became an urgent, planet-wide effort to understand what was coming and what it represented. The expanding debris cloud added complexity to every calculation. As the fragments continued moving, their interaction with solar radiation became a significant factor. Some pieces absorbed sunlight differently due to varying surface compositions. Others tumbled irregularly, producing unpredictable shifts in their trajectories over time. The gravitational influences of planets, moons, and even the subtle pressure of the solar wind further stretched the range of outcomes. But amidst the noise, a core truth solidified. If the current vector held, several pieces would intersect Earth's gravitational influence within the projected window. The implications of such an event depended entirely on the size and velocity of the incoming material. A fragment the width of a fingernail would burn up harmlessly in the atmosphere, producing nothing more than a brief streak of light across the sky. Larger objects, especially those several meters across, could survive the descent long enough to reach the ground. Their kinetic energy, multiplied by interstellar velocity, could deliver localized devastation. A fragment tens of meters wide could produce an atmospheric explosion powerful enough to flatten structures across a broad region. The uncertainty surrounding the sizes of the inbound pieces added to the tension, because only limited data existed on their estimated reflectivity and mass. Space-based telescopes strained to discern individual fragments with high precision, but the dispersal pattern and the glare of the sun complicated the effort. In time, better imagery would come, but the early stages offered only rough outlines. Scientists compared notes across continents, merging data from optical telescopes, radio arrays, and infrared sensors. Each dataset painted a slightly different picture, yet all converged on the same conclusion. The Earth was positioned in a corridor of potential impact. The mere concept of material from an interstellar object reaching Earth held profound scientific significance. Such fragments could contain compounds or isotopic ratios unlike anything native to the solar system. Their composition might carry traces of environments shaped under different stellar conditions. Studying such fragments could provide a rare glimpse into the chemistry of distant regions of the galaxy. But the potential scientific rewards did not diminish the gravity of the situation. The approach of this debris cloud demanded attention, not just as a research opportunity, but as a planetary priority. The emotional landscape across scientific institutions shifted rapidly from astonishment to determination. Researchers accustomed to methodical analysis now faced the need for rapid assessment and decisive interpretation. Every new data point fed into models that updated in real time, producing refined projections that scientists combed through with intense focus. There was a shared understanding that while the fragments were too small and numerous for any large-scale deflection strategy, early and accurate tracking could allow preparations for the moments when material reached the atmosphere. The event also underscored a broader truth about the cosmos. Interstellar objects were not passive drifters, but dynamic, sometimes volatile travelers whose behavior could defy expectations. 3I Atlas had already surprised astronomers with its composition and trajectory, but its sudden destruction introduced an entirely new category of risks associated with such objects. The explosion illuminated gaps in current monitoring capabilities and highlighted the need for more advanced early warning systems capable of detecting rapid changes in small bodies from beyond the solar system. As tracking software continued to ingest updated data, patterns emerged. The debris cloud was dispersing along a gradient of velocities, with faster pieces racing ahead and slower ones trailing behind. This created a broad temporal window for potential interactions with Earth. Impacts, if they occurred, would not be confined to a single moment, but could play out across an extended time frame. The earliest fragments on the inbound trajectory were the most difficult to characterize because they moved with high angular velocity and reflected minimal sunlight. The larger fragments, traveling more slowly, were easier to detect but carried far greater potential to reach the surface. Scientists imagined the sky as a giant canvas upon which the debris would trace invisible lines until atmospheric entry. Within research centers, teams worked to translate those invisible lines into meaningful predictions. They built confidence intervals around every potential encounter, focusing first on fragments large enough to matter. Satellite networks were prepared to cross-reference radar signatures once the debris crossed within discernible range. Astronomers running ground-based systems coordinated observation windows to avoid redundancy and maximize global coverage. Meanwhile, the pressing question of how 3I Atlas had come apart lingered in the background. The explosion was strange even by the standards of volatile small bodies. If internal stresses had caused it, those stresses must have been enormous, suggesting pockets of gas or crystalline ice under extreme pressure. If a collision triggered it, then the unseen collider must have struck at just the right angle and speed to destabilize the entire structure. Some researchers considered more exotic possibilities, such as electrostatic discharge or a dramatic thermal gradient within the object. Whatever the cause, its effects were unfolding across millions of kilometers of space, rippling outward from a point no observer had managed to capture directly. The event highlighted the vast gulf between human predictability and cosmic unpredictability. Here was a visitor from a distant star system, most likely older than the solar system itself, suddenly turning into a hazardous cloud. The explosion transformed 3I Atlas from a curiosity into a reminder that humanity's celestial neighborhood was more dynamic and occasionally more hostile than many assumed. Scientific models had long accounted for near-Earth asteroids and long-period comets, but interstellar debris represented a challenge with fewer historical precedents. The implications extended into fields that had little prior connection to the study of interstellar objects. Atmospheric scientists began modeling potential airbursts to estimate how shockwaves might propagate. Geophysicists revisited historical impact sites to better infer the consequences of collisions with objects of unusual composition. Materials scientists speculated on how interstellar compounds might behave under atmospheric heating, ablating differently from familiar meteoritic material. These interdisciplinary efforts were not speculative exercises, but urgent necessities, because every hour brought the inbound debris closer to the inner solar system. Collaborative energy intensified as agencies shared data freely. The tools and methods refined during previous near-Earth object observations proved invaluable now. Machine learning systems trained on historical meteoroid entries were repurposed to identify unusual light curves associated with incoming fragments. Observatories updated their scheduling priorities to dedicate more time to tracking the fragmented remains. Across the world, teams worked in concert with unprecedented speed. The spread of debris across the widening cone of space also introduced concerns about secondary interactions. Some pieces, depending on their trajectory, could pass close to Earth-orbiting satellites. Even small impacts at the speeds involved could damage sensitive instruments. Operators prepared contingency plans to shift orbital altitudes or orientations if necessary. Space tracking networks that normally focused on artificial debris had to incorporate natural interstellar fragments into their catalogs. The potential for cascading microcollisions in orbit, though still low, was added to the growing list of considerations that required close attention. Communication within the scientific community emphasized clarity and precision. The situation demanded neither alarm nor dismissal, but a steady stream of verified analysis. In this environment, speculation had to be grounded in data, and projections needed continuous refinement. The arrival of interstellar fragments on an inbound collision trajectory was unprecedented, and scientists understood the weight of the moment. As models grew more detailed, researchers began isolating the highest-risk fragments. These were pieces with enough mass and structural coherence to survive portions of atmospheric entry. The precise effect of each fragment depended on its angle of approach. A shallow entry might cause a long, bright streak that dissipated energy across hundreds of kilometers of atmosphere. A steep entry could produce a more concentrated energy release, potentially leading to a powerful detonation high above the surface. The variability inherent in these possibilities made prediction challenging, but prediction remained essential. Each new calculation brought humanity closer to understanding the scale of the event. The fragments themselves were remnants of a worldless wanderer, shaped by forces unknown, drifting through the galaxy for eons. For countless ages it had traveled that desolate course, untouched by life, unseen by any intelligence. Its sudden disintegration near the solar system was startling, not only for its destructive potential, but also for the reminder of how little control humans had over cosmic events. Throughout the unfolding analysis, a quiet realization threaded its way through the scientific community. Interstellar objects like 3I Atlas were not unique, nor were they vanishingly rare. They represented a broader population of nomadic masses drifting between the stars. Some were icy, others rocky, some perhaps metallic. Any one of them could follow unpredictable paths shaped by the gravitational pulls of many systems until they eventually approached new suns. This awareness added urgency to improving detection systems capable of spotting similar objects earlier. The goal was not merely to react to the debris of 3I Atlas, but to prepare for future encounters. The implications also reached into philosophical and existential territory. The debris cloud symbolized the collision between human civilization's relative stability and the vast, indifferent mechanics of the universe. It underscored the reality that the solar system existed not in a sealed bubble, but in a cosmic ocean filled with drifting remnants of distant worlds. The explosion of 3I Atlas brought a sense of scale back into focus. Humanity was witnessing the remains of something ancient, something shaped by the physics of places light years away. Even as data converged around the likely inbound path of certain fragments, the broader scientific effort took on a tone of determined readiness. The situation was not one of panic, but of intense focus. Instruments were calibrated with greater precision. Observatories extended their operational hours. New models were run with increasing frequency, each one narrowing uncertainties further. The cooperative atmosphere among researchers fostered rapid progress, ensuring that the evolving debris field was mapped as accurately as possible. The expanding awareness of the event's magnitude pushed teams to examine the fragments' characteristics more closely. Variations in reflectivity hinted at differences in composition, with some pieces appearing darker and others more crystalline. These variations affected how solar radiation nudged each piece, adding small but cumulative adjustments to their paths. Scientists accounted for these subtle effects to refine predictions, knowing that even minor changes might influence whether a fragment entered the atmosphere or missed Earth entirely. Despite the uncertainty inherent in the evolving situation, a remarkable sense of purpose guided the global response. Scientists saw in 3I Atlas not only a challenge but a rare chance to observe the behavior of interstellar material in real time. The explosion exposed inner layers never before visible, offering clues about its structure, age, and history. Its fragments, now spread across an immense region of space, represented samples of environments far beyond the reach of spacecraft. The potential knowledge embedded within them carried the weight of entire star systems. Astronomers continued tracking the movements of the debris across the darkness, their instruments tuned to catch faint flashes of sunlight glancing off their irregular surfaces. As each new coordinate set arrived, it fed into a growing database that charted the evolution of the debris field. The map, though still approximate, illustrated a sprawling, dynamic cloud that was moving simultaneously toward and past Earth. The inbound fragments represented only a portion of the whole, but their significance was profound. Every hour that passed allowed scientists to narrow the margin of uncertainty. The broad corridor of potential impact gradually sharpened into a more refined path. Some fragments drifted out of alignment with Earth's position, either due to slight perturbations or previously undetected rotation, reducing the risk they posed. Others maintained their route, their projected arrival window becoming more clearly defined. This clarity, though sobering, allowed for more disciplined planning within the scientific community. What began as an unexpected flash captured by a handful of observatories had evolved into one of the most significant celestial events ever tracked in modern history. 3I Atlas, a once distant and unassuming interstellar visitor, had become the center of a global effort to understand the behavior of a fragmented object from the depths of space. Its explosion scattered not only debris, but also a surge of new questions, new opportunities for discovery, and new appreciation for the delicate balance between Earth's stability and the vast cosmic forces beyond. The inbound fragments continued their silent approach through the vacuum, unaware of the attention fixed upon them. They drifted along ancient paths shaped by forces older than human memory, approaching a world that had no part in their creation, yet would soon feel their presence. Every piece carried with it a story etched into its atomic structure, a trace of some distant star system whose name would never be known. Their arrival, whether gentle or violent, would mark a moment of profound intersection between two cosmic narratives. The glow of data screens, the swirl of orbital predictions, and the hum of telescopes turning toward the sky formed the backdrop for this unfolding chapter. The event was far from over, and the implications were still being written in the steady accumulation of observations and calculations. The fragments of 3I Atlas continued their journey inward, unstoppable, indifferent, and ancient, while humanity stood at the edge of awareness, watching, measuring, and preparing for whatever the next stage of their passage would bring. Momentum within the scientific world intensified as the fragments of 3I Atlas silently advanced, and a new wave of observations began revealing aspects of the debris field that had gone unnoticed in the early hours. As telescopes refined their focus, researchers detected faint wisps trailing behind several fragments, thin plumes of vapor or dust that glimmered weakly in infrared wavelengths. These emissions suggested active surface processes still unfolding on the shattered remains. Even after the explosion, sublimation continued to sculpt the debris, altering their shapes and subtly influencing their motion. This realization introduced a fresh layer of complexity, because outgassing, even at a small scale, could exert unpredictable thrust on the fragments, making their trajectories drift in ways difficult to model. The plumes also hinted at the chemical richness of the object before its disintegration. Some fragments released compounds that absorbed sunlight differently from the rest, creating brightness fluctuations that flickered like distant embers. Spectrometric readings suggested the presence of exotic ices rarely found in local comets. These compounds evaporated rapidly in the sun's mild warmth, creating microjets that nudged the fragments with uneven force. Scientists recalibrated their models yet again, now factoring in transient outgassing behavior that varied not just from piece to piece but from hour to hour. The dynamic nature of the debris forced teams to abandon older assumptions about how still fragmenting objects behaved in the vacuum of space. The scaling of the debris cloud across millions of kilometers prompted agencies to coordinate new forms of observation. One initiative involved repurposing a network of radio telescopes originally used for mapping deep space pulsars. Their reception sensitivity allowed them to detect radio wave scattering caused by denser clusters of dust and tiny fragments invisible to optical sensors. As these signals accumulated, they painted a ghostly outline of the most diffuse regions of the debris field, revealing wispy arcs of dust drifting far ahead of the larger fragments. Although individually harmless, these dust streams could interact with Earth's upper atmosphere in unusual ways if they intersected the planet. Atmospheric physicists began running simulations to examine how such fine-grained material might behave, how it might ionize, and how it could influence transient high-altitude electrical phenomena. Meanwhile, a parallel concern emerged among researchers studying the orbital dynamics of artificial satellites. Not all satellites possess sufficient shielding to withstand even tiny collisions with hypervelocity dust. Although the probability of a direct encounter remained small, the sheer volume of ultrafine debris made the risk impossible to ignore. Mission controllers reviewed contingency procedures in case sudden reconfiguration of satellite orientations became necessary. They prepared to shift certain spacecraft into safer operating modes to minimize cross-sectional exposure. The possibility that interstellar dust could interfere with communication systems was also considered, prompting engineers to conduct stress tests on signal resilience in case the ionized trail of a dust fragment happened to intersect radio pathways. Each fragment carried its own evolving story as it tumbled through the emptiness between the planets. Some of the larger pieces began exhibiting rotational patterns that were far more irregular than those seen in local comets. Rather than simple rotations, several fragments spun along multiple axes simultaneously, creating chaotic, tumbling motions. This tumbling affected how sunlight warmed their surfaces, sometimes creating abrupt thermal bursts on one side that altered their trajectory in sudden, unpredictable increments. Scientists realized that even slight modifications in sunlight exposure could produce measurable shifts. and they began tracking rotational signatures to better anticipate how each fragment might behave. New algorithms were developed to model the chaotic spin states, pushing computational resources to their limits. Researchers studying the evolutionary history of interstellar bodies saw in these rotational patterns clues about the stresses the original object had endured over untold millennia. The erratic spin suggested earlier collisions or interactions with gravitational tides near dense regions of space. Some fragments exhibited surface features resembling fused layers, as though the object had once passed through zones of intense radiation or grain-rich clouds that battered its exterior. Every new observation seemed to peel back another layer of cosmic history, revealing that 3I Atlas had been shaped by journeys far more tumultuous than initially believed. At the same time, interest grew among cosmochemists who speculated about the internal composition of the fragments. The explosion had exposed deep material that would never have been visible otherwise. If any portion of these fragments entered the atmosphere, even briefly, instruments on the ground might capture spectral imprints that hinted at their internal chemistry. Discussions arose about preparing high-speed spectrographic stations capable of analyzing transient streaks of light produced by atmospheric heating. Detecting rare isotopes or unusual organic compounds could provide unprecedented insight into distant stellar nurseries and planetary systems that once shaped the interstellar traveler. Even as these scientific prospects expanded, attention remained anchored to the inbound trajectory. The fragments that continued to hold their course created a narrow but well-defined region of focus across multiple observatories. The more precisely these fragments were tracked, the more tightly the uncertainty envelopes shrank around their expected path. A hierarchy of risk began to emerge, though it remained fluid. Some fragments were large enough to warrant close surveillance, yet they remained too faint for many telescopes to track continuously. Others, though brighter, were small enough that they posed minimal threat, but still carried important scientific value. A growing sense of urgency filtered into meetings among planetary defense experts as they recognized that even accurate projections required continuous confirmation. The dynamic nature of the fragments meant that predictions could shift hour by hour. Automated monitoring systems were adapted to flag any sudden deviations, particularly those that might imply new outgassing events or fragment collisions within the debris field itself. Even a small collision could send a piece spiraling unpredictably, and scientists knew that such changes could cascade into entirely new trajectories. As the measuring instruments grew more sensitive, researchers captured detailed albedo maps of several fragments. These maps revealed stark contrasts between glossy crystalline regions and matte, carbon-rich patches. The crystalline regions refracted sunlight into sharp flashes that flickered unpredictably, while the darker patches absorbed heat, creating pronounced thermal gradients. This combination of properties implied that the original object had undergone cycles of heating and cooling in different stellar environments throughout its ancient journey. The presence of crystalline formations hinted that 3I Atlas might have once passed relatively close to stars hotter than the Sun, where intense radiation could have reshaped its outer layers. Meanwhile, the carbon-rich patches suggested long epochs spent drifting through colder interstellar voids where carbon compounds condensed on its surface. The more scientists learned, the more they recognized that 3I Atlas was not merely a relic. It was a witness to cosmic epochs far beyond the timeline of the solar system. Its fragments represented geological chapters from regions of the galaxy where human instruments could not readily peer. This realization lent a sense of gravity to every dataset transmitted from observatories around the world. The fragments were not only potential hazards, but also messengers from ancient interstellar realms. As the inbound window approached, atmospheric physicists identified another concern: the possibility of upper atmospheric ionization anomalies triggered by the passage of particularly volatile fragments through the magnetosphere. Even without an atmospheric entry, fragments skimming near the planet's magnetic boundary could shed charged particles that interacted with Earth's field lines. While not dangerous, such interactions could create short-lived disturbances similar to those caused by solar storms. This possibility prompted additional monitoring of magnetospheric data to ensure that any unusual readings were correctly attributed to fragment passage rather than internal disruptions. An unexpected development emerged when astronomers detected a smaller, fast-moving cluster within the debris cloud whose motion did not match the trajectories of surrounding pieces. This cluster appeared to be composed of fragments that had broken off during a secondary disintegration event after the initial explosion. Their accelerated drift suggested internal processes still active within the debris, potentially releasing trapped gases that further fractured weaker pieces. These secondary fragments, though small, provided clues about the structural diversity within the original object. They may have come from a region rich in layered volatiles or brittle materials prone to microcracking. The slow expansion of this cluster prompted scientists to track it carefully, because its behavior differed markedly from the more stable fragments. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 3I Atlas exploding and debris heading toward Earth and humanity? We want to hear from you. Thank you for watching, and see you next time.